recording. Okay, so chapter 6 is going to be on this thing called operational amplifiers. So you guys will be building amplifiers in lab 4 at the end, but then you're going to find out that that amplifier is kind of like super hard to work with. Okay, using just pure transistors. Okay, and so we went through transistor very quickly last week, and you guys are doing a lab on it. And the nice thing about transistor is that it can be made very cheaply and very small. Okay, but in reality, right, when you're working on a breadboard, okay, being small and cheap is not, well, cheap at the level of like a few pennies, right? Where operational amplifiers are like 50 cents. Okay, so but if you're working on, for example, the EOS project, which has a budget of $10 million, right? 50 cents is not too bad to spend on an amplifier. So, and the idea for these operational amplifier is to make it so it's easy to work with. Okay, and we're going to see why it's easy to work with once we have these golden rules for operational amplifier. Okay. And this is going to be the most useful device that you're going to, or maybe not the most useful, the most common device that you will use in the future if you decide to do any experiment or do any electrical engineering in the future, any job where you're prototyping something, meaning you're just building something once to just make sure see how it works, right? And it's going to be the most useful device when you're learning in analog electronics, because it's the simplest solution to like 99% of the problems. Okay, it may cost a little bit more, but then instead of saving 43 cents on a transistor, right, to make it work and spend 3 hours on it, right, you can just plug in the op amp. It will just work in about a minute. Okay, so you're just saving time with that. Okay, and op amps are also the basis for digital electronics, which is where we're going to start in about 3 weeks. Okay, in chapter 7. Okay, so as a student, same for me, when I was a student, we get to use the LF411. In fact, there's a bunch of them in your kit right now. They look like little spiders like this. In fact, they also have 8 legs. Wait, do spiders have 8 legs? Yeah. Oh, they're octopus. Okay. Yeah, 8 legs. Okay. They look like little black dot like this. They're like, maybe not even 50 cents. They're like probably like 20 cents each when you buy them in bulk. Okay. Right? And it's your first integrated circuit, meaning inside this little chip, right, there are multiple things in there. Okay, it's just kind of hidden away from you. Okay, before we go dive inside the chip itself, what we want to do is just kind of have you guys stare at this picture, right? One of the things to note is that there's this little circle thing on the left, right, or a notch, depending on who makes the LF411 or any integrated circuit for any chips. Okay, these are usually indicators for pin number 1. Okay, so because you can rotate this upside down and have no idea where the pins are, right? So either the little circle or a little notch at the end tells you which way is kind of up on the chip. Okay, all right. Input number 1 is actually super not useful. It's called the balance. It allows you to kind of tweak the difference between the inverting and non-inverting input, and we're gonna talk about what these inputs are actually doing. Okay, the first thing you want to actually learn how to use is the voltage power supply, which is known as VCC, voltage constant C. I don't know what the other C actually stands for. And then that's going to be from your breadboard. Okay, the voltage power supply is going to be from your breadboard, because your breadboard is very good. Right, let me pull this out. Disconnect all my probes. Ooh. I'm really glad. I'm sure the you guys watching this at home later will appreciate all this time you're spending looking at stuff that you can't see, right? So remember on our first lab, we used these as our power supply, right? On our second and third lab, we use the function generator as our AC source, right? And I keep telling you, don't mix those two things up, okay? You have to keep track that, okay? So VCC, you want to supply with the constant voltage, right? And then whatever input you put in here is going to be your AC or your function generator. Okay? Keep those separate. They do have to share a ground. Okay? And that way it knows what the 0 point of your device is. Okay? There's an output over here, but let's not talk too much about detail about exactly what these things are until I can actually tell you how these things actually behave. Down here is just another picture. So inside your LF411, if we go over here, okay, this is the schematic inside that chip. You actually don't need to know this, but it's just a good idea to kind of get a picture of how many things are inside here. Okay, so hopefully you guys recognize this. What is this? Okay, what about this one? So this is a PNP transistor. What do you think this one is? NP. Sorry, this is the NPN. This is the PNP. Yeah, right. When the arrow goes into the transistor, is the PNP. Okay. What about these little boxy thing? Anyone knows what these look like? It has 3 things attached to it. Okay. Right. This has 3 things attached to it, so this will be very similar to each other, right? These are actually field effect transistors, the ones I talked about that that are easier to make on a wafer, but we don't actually use it because they're just less they're less intuitive in their usage. Okay, because basically you're using the voltage difference between here to determine what the output is. Okay, and then you got some diodes, right? These are gonna work with these today, and then some resistors and some capacitors, some diodes. Okay, so inside here there's 1 transistor, 2 transistor, 3, 4, 5, 6 transistor. There's 6 transistor in the chip itself. Okay, plus 3 diodes and then a couple of capacitors and a couple of resistors. Okay, so all of this got integrated together into a little black block, right? The size of a little bug for you. Okay, that's why these are called integrated circuit. Okay, they're integrated circuit. Okay, or known as IC. Okay, right. Okay, right. In order for you to understand why this is more useful compared to a transistor, because you think that, oh, it's operational amplifier. I mean, I can amplify stuff with my transistor, right? The transistor you're going to use today, right? What happened is that this beta factor that I have you guys calculate in the pre-lab, right? You use a number 100, right? Okay, you're going to see today in lab is never going to be it's never going to be exactly 100. It's going to be like 80, 120, and then if you even ramp the current even higher, you're going to turn up to be like 200. So it changes on you, which is really nasty when you want to amplify the current by a factor of 100, but then you're amplifying by a factor of 200 instead, and now your computer doesn't work anymore because you draw too much current, and then you blew up your screen or something like that. Okay. So for example, if you have a very small current passing through on your base current, if you just multiply that, remember the idea is that, right, the base current is going to be actually the emitter current, right, is about 100 times bigger than your base current, right? Right. Technically, there's a 1 plus there, but just ignore that 1 plus, right? It's going to be the same number. Okay. So so when you have a small current at your base, right, you're going to have maybe a beta of exactly 100. Okay. But if you increase that by a factor of 10, you're going to get a beta of 200 instead. Okay. And this is due to the fact that what happened is that, remember what the principle of a transistor is that you have a very thin P layer, right? And you're depending on a lot of these charges to go back to the base, right? Right, let's say this is go back to the base, oops, as opposed to passing through to the emitter, right? Okay? And what happened is that if you put too much base current in, then you just get an avalanche of electron passing through your transistor instead, okay? And that's why the beta is strongly dependent on on basically the base current, which is not good, right? If you don't have a beta of 100, right, you're going to have different application depending on how much current you're driving through your thing. Okay, so typically in our as you know, usually as like, you know, science level people, right, and even a lot of engineers, we're not going to use transistors directly. Okay, if you were like an well-trained electrical engineer and trying to design processors for Intel, you would be using transistor because transistors are cheap and small, right? Right? As opposed to an op amp where a factor of 20 in the cost, right? It'll make your processor cost $20,000 instead of $200, right? That's a huge difference, right? So if you see if you know, go in your phone or your computer, hammer that, and then take out the motherboard and take out the processor, and then hammer that and put it under a microscope, you see all these little, you know, tiny things in there. What you'll see, all these are even transistors that you can't even see, actually, even under a microscope, right? You need an electron microscope to see them, okay? And that's how small these things are now, okay? But for us, okay, an operational amplifier is useful because it allows us to use this thing called negative feedback, okay? And this is a completely new concept, okay, that applies to operational amplifiers. That's going to be extremely important for us to understand because it's sort of like the key difference between transistors and operational amplifier. Figuring out how to use this thing called a negative feedback, okay? So negative feedback was this idea was from this guy Harold Black, who works at Bell Lab. Yeah, Bell Lab, and he's involved in. Well, anyone recognize this picture? Where's this from? I'm sorry. Landing on the moon. Yeah. So it's the Apollo mission, right? Okay. Apollo mission. Okay. So Harold Black is an electrical engineer, right? Why would he be involved in the Apollo mission, sending people to the moon? Go to moon. What do you guys think? Electronics. What else? Yes, signals, right? Okay. So until, you know, 19 up to 1960, the furthest people have talked is from away from each other is like across the Atlantic, right? You know, a couple of thousand miles, right? How far is Earth to the moon? I think this is in kilometers. Okay. So you can figure out that, oh, why amplifying a signal is very important, right? Okay. And he came up with this idea in order to, for Earth, you know, NASA, right, to communicate, communicate with astronauts. Okay. And that's what he's famous for. In fact, before this, before operational amplifiers, people use these things called vacuum tubes. Do you know what vacuum tubes are? You ever heard of those things? To amplify signal. And each vacuum tube is basically going to be the size of this bottle, right? Right? So imagine how much space you will save by replacing one of these with one of these on a space mission, right? How much weight you save also, right? Right? So so we would not be able to actually get to the moon without the contribution from operational amplifiers and this idea of negative feedback from Harold Black. Okay, in fact, uh, I think I don't remember exactly the story of Harold Black, how he came up with the idea, but we actually use this every day. Okay, how many of you guys drive to school? Not a lot of you. Okay, some of you. How many of you guys walk to anywhere? Walk anywhere? Okay, so you're using negative feedback yourself in this case. Okay, so I'm going to do the driving example. So let's say you're on a two-lane road, dot 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 dash in the middle, right? You're in the car, right? It's wheels, okay, all right, okay. You're in the car. You can see that. Well, the car. Let's say you know you start to drift off to the left, okay? Right? When you drift off to the left, what do? You turn right, right? When you drift to the left, or up in this case, right, you turn your steering wheel to the right, right? So you do opposite of what you observe, right? Because if you start drifting left and you turn to the left, that makes it worse, right? Okay? So, so the idea is that whatever you observe, right, you do the opposite to correct it, right? Same thing with your walking, right? If you're walking, in the wrong, too far to the left and where all the goose poops are, right? You walk towards the right, okay? Right? So what happened is that, if you turn your steering wheel to the right, and now you overcorrect it, now you're too far to the right, right? What do? You turn left, but a little bit less, right? And therefore now you correct it yourself so it stay in the lane, right? Just, it's an iterative process, okay? Hopefully you don't do this too much in the road. It'll just kind of worry a lot of people, okay? And this is also why, right, when you're drunk, not that anyone does that, right? Right? When you get drunk, your response time is a lot slower. Therefore, you're making these correction a lot slower. That's why you're swerving left and right, right? When you're sober, then you can make these correction in, maybe like, 200, 300 milliseconds, which, makes it so that you're not swerving too much. Operation amplifier works on the same principle, at least on this negative feedback um, um, mode, okay? Okay? But before I can tell you how negative feedback comes into it, let's describe what an operational amplifier does, okay? So as you saw from the picture above, right, there's some voltage, right, that you have an input and an output on, right? Sorry, a voltage, a constant voltage source for positive voltage, and either ground or a negative voltage source, okay? So if you look on your breadboard, you see that there's a positive 15 and there's a negative 15. So you can actually go positive and negative 15, okay? So this is 12 to 15 volts positive, right? This can be 0 to negative 15 volts, okay? Negative, okay? Right, and there's two inputs to your operational amplifier. There's a thing called a non-inverting input, okay? Unfortunately, this is known as V plus, okay? Don't mix this up with VCC. VCC and V plus are very different from each other, okay? If you connect the other two, you're gonna end up on the wall of shame. And unfortunately, this wall is pretty small. So these are people who connect them the wrong way, and they just burn out their op amp, and now they have to come and ask me for another one. You did that already? Yeah. Okay. All right. And then there's the output for the operation amplifier. Let's describe how these things are related to each other, okay? All right. So these are the rules that the book give you. I'm going to go through what the book rule does, but I'm going to give you a different version of it, my little golden path, and which is only 2 rules, okay? The book has 7 for some reason, okay? There is some important points about this, but we're not in application. You don't actually think about it too much, okay? Okay. This first line here is this: the open loop voltage gain is infinite, meaning, okay, this output can go from 0 to infinity at like 0 time. Okay, you can ramp the output from negative infinity to positive infinity at almost no time, which is idealized, right? It's not realistic, and we're going to see how this turns out the next lecture on Monday. Okay. What's important is that the input impedance of the operational amplifier is infinite. Okay. So these are the input, right? Okay. Meaning, right, when you connect these to like a voltage, right, there shouldn't be any current going into the input, right? If you have infinite impedance, right, it's like the current is running into a wall, right? Okay, so I want to picture that, okay? Even though it's not true. I keep saying these things. In theory, right, you should use it like that. It does take a little bit of the current in order to sample what the voltage is, okay? Remember on your multimeter when we first talked on the first lab, right? Right? the way that your voltmeter measure voltage is by taking a little bit of current out of your circuit in order to sample how much current goes through with a certain resistance, right? That's how it measures voltage. Okay. The output impedance, which is up on this side, is 0. Okay. It doesn't. In reality, it may be like, you know, as opposed to the input impedance being infinite, right? It may be like 100 meg ohm. Okay. In reality. Okay. As opposed to the output impedance being 0, it may be like 1 ohm. Okay. So it's not absolute. Okay. Okay. The op amp can change the output voltage instantly. Okay. This is known as a slew rate, and we're going to talk about this on Monday. But that means, you know, this output can swing from negative infinity to positive infinity as much as you want without affecting it. These are all idealized systems. Okay, these are idealized op amps. Okay. All right, and it's going to make the input, the two input, exactly the same voltage. Okay, that means V plus and V minus. The op amp is going to do its best in order to make those the same. Okay, and you're going to see why this is useful when we talk about negative feedback with it. Okay. Okay. The operation doesn't depend on temperature. It doesn't vary with voltage source supplies. Okay. So these are just like, oh, you know, very, very idealized op amps. Okay. Okay. All right. So with this, what I'm going to tell you is that the two rules that I remember. I don't remember these 7 things. Okay. So I'm going to call them the golden rules of op amps. Okay. Instead of the golden rules for transistors. Okay. The golden rules of op amp is that, right, no current flows through the inputs of the op amp. Okay. This is actually the same rule as number 2. Okay. This is basically the same as number 2. Okay. Why is that the same? Anyone want to tell me? Maybe on the left here. Why is my golden rule number 1 basically the book's rule number 2? I'm gonna grab a snack while someone talks. Any idea, Alwyn or Uriel? Right. If your impedance is infinite, right? Think about it as just, you know, the current's running into a wall, right? The current cannot get into the inputs. Okay. Okay. And then golden rule number 2 is that the op amp is gonna try to force V plus and V minus to be exactly the same. Okay. So this is basically, you know, the book's version of number 5. Okay. And those are the 2 important things. Okay. For you to remember when you're using op amps. Okay. So let's see how this what happens here when we have just connect this circuit operation amplifier like this. Oh, these are pretty good. Sorry. Okay. So this is this little triangle represents an op amp. The positive means the non-inverting input. The negative means the inverting input. Okay. And all we did is we connected the output with a wire to the negative, the inverting input. Okay. And our AC source is coming in at the non-inverting input. Okay. Okay. So try to use this word non-inverting input and inverting input as opposed to V plus and V minus, because that's always confusing. Because V plus and V minus makes me think about positive voltage supplies and negative voltage supply, right? Okay. Okay. Typically, what will happen is that the the diagrams will skip the VCC and VEE connection. They just say, okay, it's implicit that you're gonna power these things up. Okay. Okay. So, how would this circuit behave? Okay. So let's follow the 2 golden rules, right? Well, no current flows into the input of the op amps, so that means whatever voltage here, right, right. If no current flows through here, right, V in is going to be exactly what V plus is, okay, right. So if V in is 10 volts, V plus is going to be set to 10 volts, right. Rule number 2 is that the op amp is going to try to force plus the inverting and non-inverting input to be the same, right? So if V in is at 10, V plus is at 10, right? It's going to make V minus to be 10, right? Does that make sense? So, right, that V in is 10, V plus is 10, V minus is 10, V out is, well, one more line. And since V minus is connected to the output, right, it's going to force V out to be 10 also, right? Mm-hmm. What would you call this amplifier? What would you call this circuit to be? If I was to draw, let's say, X and Y, time, voltage, right? If my input is like this, right, what would my output look like if the op amp is powered up? David, seems like you want to answer. The same, yeah, great, exactly the same, okay? Okay, and this is why this is called an op amp follower, right? It just, the output just follows the input, okay? Okay, right, not too interesting, right? Okay, just like the transistor follower, right? It was not too interesting, but it's just to get the concept across, okay? Let's do something a little bit more interesting. Let's do an inverting amplifier, okay? Without even knowing what the circuit, without analyzing the circuit, right? What do you think this circuit is going to do? It's going to amplify the signal and does what? And flip it upside down, okay? Okay. So let's see how this happens, okay? Okay, I'm going to copy down rule number 1, right? No current at the input, at the inputs, 2 of them. Number 2 is that V plus equal V minus, or at least try, okay? Okay, those are the 2 rules. Huh? Once again, right, they skip the VCC and VEE, so don't get confused by that. You just assume that these op amps are powered up, right? Okay. All right. So in here we have a input resistor connected to the the inverting input. So notice that they flipped this upside down on you, right? Be careful about that. Okay. So they can orient the plus on top or the minus on top, right? But also, right, there's a wire connected to a RF, a feedback resistor, to the output, okay? And this is where we're going to start seeing this thing called negative feedback, okay? Okay? It's the feedback, right, that goes back to the input, okay? All right, how do we figure this out? Okay? So rule number 1 is that, well, no current flows into the inputs, right? So whatever current flows in here, right, it gets stopped by here and it has to go through both resistors, right? Whatever the current from V in to V minus, right, it has to go through this loop, okay? The only path for the current to go, right, I'm going to highlight that in yellow, right, is this way, right? This is the only path for the current, okay, right? In fact, this is going to be called IF, right? And then we can call this, I in, for example. So there's a lot of I's. Okay? Okay. Rule number 2 is that it's going to try to make the non-inverting and the inverting input the same. How is that going to be useful for us? What has to be the voltage at the V minus, or AKA the non-inverting input? What does that voltage has to be with rule number 2? Someone in the middle? The voltage at at where? I'm looking for a number actually. Eddie, Josue, Shane? Is 0. Why is it 0? Well, no, it's not. I'm asking for the inverting input. It's not tied to ground. The non-inverting input is tied to ground. Yeah. So the non-inverting input is tied to ground, but if you obey Rule number 2 is going to force the inverting input to be ground also, right? So this is always going to be at 0, okay, or tries to be, okay? So that makes it nice because right now I know exactly what I in is going to be, right? Because if I have V in going through a resistor to go to 0, I can calculate what that voltage, sorry, what that current is, right? Because Ohm's law, right, this is something that, right, V equals IR, but this is actually the voltage drop. The voltage drop meaning V in minus 0, right, across that resistor is going to be the current through that the input current times Rn, right? Right? It's not, well, you know, that zero's there, so it just disappeared, okay? So exactly I know what In is. Okay, I'm going to use the capital even though it's a time-dependent current, um, but we're going to see that this is directly applicable to the time-dependent current also. Okay, so In is that, okay? Well, how is that related to the output, right? It's related to the output somehow through this feedback resistor, right? So we have to figure out what IF is. What the hell is IF? Okay, a variable on this board, it will be IF. Okay, it's correct. It is IN. Someone else tell me which rule. You have 50-50 chance to get it right. Why is IF and IN the same? Okay, which rule? Number 1 or number 2? Number 1. Why? Right, the current can't go this way, so it has to go out through this way, right? Exactly. All right. So that means this is also equal to IF. Okay. And since we're declaring that the current is flowing this way, just by our declaration, right? Right? How can we calculate V out? V out is equal to what? What should be on the right-hand side here? Right. Which I? RF. Exactly. Right. So there is this negative sign, okay? But I know what IF is, so I can plug that over here. So negative V out is equal to V in over Rn RF, right? In other words, V out is negative. I'm going to squish these two together. RF over Rn times V in, right? What is this? What's negative RF over Rn in our Lab 3 language? It's the gain, right? Okay. So if your RF is 10 kilo ohm, your Rn is 1 kilo ohm, you get a gain of negative 10, right? Right. And then if your RF is 1 kilo ohm, your Rn is 10 kilo ohm, you get a gain of negative 0.1, right? You can even make this signal smaller, okay? And it's just by swapping these resistors in and out, you can change whatever gain you want, which is pretty nice, okay? Unfortunately, this flips the signal upside down, right? So before I move on, any questions about this? How you analyze this? By just looking at these two rules and try to apply them. It's like a little puzzle. Yeah, Shane?
Just curious, where does the zero come from when you go zero minus V out?
0 minus V out, right? So V in minus, so remember Ohm's law is that the change in voltage, right, gives you the current times the resistance, right? The change in current V in to 0, right, because the reason this is 0 is because the plus is equal to 0, and that's because of rule number 2, right? And that's where that comes from, okay? You know exactly what voltage is here because you connected this input to ground, right? Okay, and that gives you a set voltage point so you can do delta V's everywhere, right? Okay, or technically it's not delta V, it's voltage drops everywhere, okay? It's negative delta V. Okay, so I'm gonna let you guys do the non-inverting amplifier in your homework, okay? All right, the gain you're gonna get is gonna be 1 plus R1 over R2, okay? All right, and in this case, right, now we have V in going into the plus, the non-inverting input, and then the negative sides have all these little resistors attached to them, okay? So look at this circuit and apply rule number 1 and rule number 2 to it and see what you will get, okay? All right? All right. I'm going to do a little bit the more complicated version, which is known as a differential amplifier. Okay, I'm going to make sure I'm going to do this with the path of least resistance because I only have 10 minutes left. Okay, okay. So a differential amplifier is nice because, right, as you see in your lab already, right, let me go and do this in black. Actually, come on, erase. Erase, erase, okay, right, right. When you have like an input, for example, right, like this, right, you never actually see it completely clean, right? Some of you guys, I've seen this, right? You have a little fuzziness to your signal, right? You guys seen this yourself, right? What is this fuzziness? This fuzziness comes from noise in the line, right? You know, someone's cell phone is close to you, there's a bunch of Wi-Fi signal going around, right? So what this is actually showing you is a combination of your original nice clean signal, right, plus a little bit of noise. Okay, if you break this up into two component, right? If you add the blue and the green here, you get this, right? You just get, right? Okay. So a differential amplifier can remove this noise. Okay. Okay. Right. This is also known as a common mode amplifier. It means if you have the same common thing on two, you can not only can it remove noise. Let's say you don't even want the sine wave. If you put both input with those sine waves, it will actually cancel those out. Okay, right. So let's see how this thing works. So it's a little bit more complicated. So now we have, instead of two resistors, we have four, R1, R2, R3, R4, and it's all connected in this, you know, crazy way. Okay, and this V1 here, right, that's input number 1. V2 here is input number 2, okay? So you have two inputs. One of them is going to be your noise only. The other one is actually the signal plus noise that you want to keep, okay? And the output comes out here, all right? All right, so I'm going to write what the goal is. The goal, I'm going to do that in a darker color. Let's do that in black. The goal is that we're going to find that the gain is going to be equal to, um, oops, um, the gain is going to be proportional to the difference between V2 minus V1, okay? The difference between the two, okay? Because that's what you want, right? Because you want to um, find a way to basically, if this is your V2, this is your V1, right? You want to subtract out this V1, okay? All right. Once again, right? The thing you always want to write down when you do this, okay? Rule number 1 is what? What's rule number 1? Input draws no current. Input, no current. You don't even need to write this in English, okay? All right, what's rule number 2? Right, right. The op-amp's going to try to make those input the same, okay? All right, let's see how we can derive this, okay? So I'm going to take this one piece at a time, okay? I'm going to look at only this part, only, okay? Okay. So this little circuit here, right, is V2, right, going through a resistor R2, right, and then connecting to the V plus part, but then there's a resistor to ground. Okay, what does this remind you of? Two resistor linked together like this. the voltage divider, right? So we know how to calculate the voltage divider, okay? In fact, um, I'm going to use the same language as the book, where they just define this V plus to be VB, okay? Okay. So I know what VB is in terms of V2, because it's just a voltage divider, R4, R2 plus R4. Remember this? Okay. Remember I torture you guys with this in the first pre-lab and the first lab, right? The torture is to get you to remember this, because you're going to use this all the time, okay? Two things connected to each other, figure out what the voltage is between them, is the voltage divider, okay? All right. All right, so that's our first little equation, okay? Okay, so now we're gonna go to this feedback loop. So, you know, R3 is essentially the feedback, right? This negative feedback resistor. All right, so let's go to, if we look at that part of the circuit, what do we see? We got R1 here, right? Going to the negative input, and the book calls it VA, and then R3 here, right? And then V out, okay? Right, okay? So then this is V1, okay? Right? This is basically the top half of a inverting amplifier, right? Okay. So unfortunately, right, VA is not tied to ground anymore, right? VA is going to be whatever VB is, but VB is this, right? This complicated equation. All right. So what we need to do is just we're gonna have to carry these equations around. Okay. So that means, right, whatever current flows through resistor 1 is going to flow through resistor 3, right? I'm going to call this IF, right? Right, the feedback current, right? So what that's going to equal to is that, well, VA, oops, sorry, the voltage drop across this, right, V1 minus VA, right, that's going to give me the current across resistor 1, but I know the current across resistor 1 is going to be the current across resistor 3, right, because the input from rule number 1, and that's equal to IF. Okay, and that's going to be R1. You guys follow me? Okay, because this is going to be, you know, we just need to set this problem up, and then it's just all algebra after that point, okay? Right, just like a lot of physics problem, okay? Okay, so the other side of this, right, so that's this part, oops, right, that's this part, right, that's this equation here. Now we're going to deal with this part, right? Okay. The little green part tells us that, well, whatever VA is, ooh, I'm going to write in the, whatever VA is, right, the voltage drop from here to V out, right, that's going to be the feedback current times R3, right? Okay. I see people are frowning their faces. It's like, right? Just look at this one little tiny piece at a time, right? Right? I'm just looking at this little part, right? This part, right? From VA, right? If I have VA here, right, I define that variable, right? Wherever the voltage drop from VA to V out, meaning VA minus V out, is equal to R3 times the feedback current, right? That's just Ohm's law. Okay. Now we've got a bunch of equations, so we're gonna maybe highlight the other one also. Wait, what's going on here? Why did you disappear? Right. Okay. Right. So what we're gonna do is we're gonna solve this equation for IF. So IF here is going to be VA minus V out. Now we're just doing algebra, okay? All the electronic stuff is gone. Now we're just doing math, okay? Welcome back to your, I don't know, like junior year of high school, okay? I'm going to plug that back up to here. Okay? So that means V1 minus VA equals to VA minus V out over R3. All of that multiplied by R1. Ugh. Ugliness. It is terrible. Okay. What I'm going to do is I'm going to even simplify this by multiplying R1 into here. Okay, VA R1 over R3 minus V out R1 over R3. Okay, may not make a lot of sense yet, but we're going to see that how that's going to be useful. Okay. Right. Okay. I'm going to keep massaging this because we want to eventually get to V1 by itself. Okay. So if I move this to the right, right, that means V1 equals to VA, right, plus VA R1 over R3 minus V out R1 over R3. Ugh. Okay. I'm going to do one more step here. I'm going to multiply both sides by R3 just to make things a little cleaner, because that will cancel out these guys down the bottom, right? I don't have to deal with fractions anymore. Right? Alright, yeah, now we can. Okay. What I'm going to do is I'm going to combine terms here. Okay. Let's see. VA. So VA times R1 plus R3, right, is equal to V out times R1, right? I'm just combining these two terms. Okay. What I'm going to do is I'm going to divide both sides by R1 plus R3. This may not be the shortest path forward, actually. R1 plus R3. Okay. Right. Because what I'm trying to do is to basically select out these VAs and VB, because I know eventually I'm going to use rule number 2 to make them equal to each other, right? Okay. So if you solve this equation, so these cancel out, right? But then, you still have this factor here, right? If you solve this for VA, what you will get is that it's going to be V1, this crazy ratio from this side, R1 plus R3, right? And then you still have this V out here because you moved it to the other side. Now it becomes positive. V out R1 over R1 plus R3. Now we got VA. And what's VA equals to? Tell me. Why are we solving for VA in the first place? It's going to be equal to what on this board? Nope. VA is V out times something plus V1. Right? What is it going to be equal to? Which rule are we using? VB, right? Okay, the op amp's going to make VA and VB the same. Okay, so all of this is going to equal to VB, okay, which is V2 R4 over R2 plus R4. Okay, and it's actually this and this you want, right? Yeah. If you know what if you know what all the resistor value is, and you know V2 and V1, you know exactly what V out is, right? Okay. So this is going to be a complicated equation to solve unless, okay, we do one thing to simplify it, okay? Okay, let's make, where am I? Let's make R1 equal to R2. So basically the same resistor, make these resistors the same, and make these resistors the same, R3 and R4 the same. Okay, because that'll simplify the equation quite a bit. Because right now you have 4 different variables, and then you're going to have, yeah, there's no way to solve this equation without that, okay? So just to make everything 1 and 3, I guess we get rid of all the 2s and 4s. So basically here, right, let's bring it up here, okay, V2, instead of R4, let's just, since it's equal to R3, right, And this is a particular case, okay? So those resistors don't necessarily have to be the same, but then you're gonna have this complicated equation to solve, okay? If you make them the same, we're gonna get a result that's gonna be, solvable at least, algebraically, okay? 1 and R3, because what you can see here is that you notice that a lot of these factors are the same. Go to plus R3, right? Immediately, all the denominator goes away, right? They all have the same denominator on both sides of the equation, okay? And then what I can do is subtract both sides, move V1 over, right? V2 times R3 minus V1 times R3 is going to be V out times R1, okay? Divide both sides by R3, right? V1, oops, V1, V2 minus V1, right, is equal to R1 over R3 times V out. Okay, so this is the differential gain, right? Whatever the difference between 1 and 2 is going to be multiplied by the ratio of R1 and 3, right? And that'll give you the output. Actually, right, usually when we solve these things, we want output as the function of input, right? So let's just flip this the other way. That's actually the answer, right? Okay. Happy? Right? So the strategy is that, right, you have your two rules, right? You stare at one little piece of it, you try to figure out what's going on with one of the input, and then you try to figure out what's going on with the other input. You try to figure out what's going on, right, in the equation to figure out what's going on with the output, and then these will be linked together somehow, right, using these two rules, right? That's always the strategy. Okay, I'm a little bit over, so I think I'm gonna save the adder circuit for Monday. So today, let's get started with the lab.